Welcome to the lecture on Pre-Calculus Section 6.1. In this lecture, I will introduce exponential and logarithmic functions. So first, we're going to talk about the exponential function. By definition, a function of this form, f of x is equal to b raised to the x power, where b is a fixed real number, b is greater than 0, b is not equal to 1, is called a base b exponential function. So let's break this down a little bit. So I've got the function f of x is equal to b raised to the x power. B is your base. B has to be greater than 0, so that means it's a positive number. And since it's greater than 0, that means it cannot be 0. And the other limitation is b cannot be equal to 1. All right? Then we say that the x is your variable, and there aren't any limitations on your variable, so the domain is x can be anywhere between negative infinity to positive infinity, so your domain is all real numbers. Let's briefly discuss why we have the limitation that the base cannot be 0. So we don't have a limitation on x. X is all real numbers. The domain of x is all real numbers. Let's investigate what if b could be 0. Then our function would be f of x is equal to b to the x, where b is 0, 0 to the x. Well, if x is all real numbers, it means we could have negative x's. Whenever you have a negative number in the power position, it's telling you that you're moving this number down into the denominator. That's what a negative power does. So this first one here, if x is negative 1, that means you're putting 0 to the first power down in the denominator. Right there, that's a problem. Having a 0 in the denominator makes this an undefined function over all real numbers. Okay, so we can't have b is equal to 0 as the base over a domain negative infinity to positive number. So b must be greater than 0. So let's just illustrate what would happen if you had a negative base briefly. So let's say arbitrarily I'm going to choose a base of negative 2. So our power function, our exponential function would say f of x would equal to negative 2 raised to the x. So I just arbitrarily chose some representative x values and then calculated the associated y values. All right, and let's just examine what's happening here. So we're going from positive to negative to positive to negative to positive. So your function is vacillating back and forth across the x-axis in some way. Okay, so remember the definition of one-to-one says that you can't cut through your graph passing a horizontal line through in more than one place. Okay, when you have a function that vacillates back and forth like that, then you are going to have places where it's not going to pass the horizontal line test and it won't be one-to-one. So we want this function to be invertible, so therefore a negative base will not allow it to be an invertible function. All right, let's take a look at the last restriction here, is that your base cannot be 1. Okay, so base cannot be 1. Now, this is a little easier to see. If the base is 1 and I raise it to any power, any negative power is going to bring 1 into the bottom, and it'll be raised to whatever, like if this was a 3, let's just put a 3 here, I'd have 1 in the bottom cubed. All right, that's still 1. All right, and any time you put in any number here, whatever it is for x, you're raising 1 to that power, and you're still going to get 1. So you can see you're going to have 1, 1, 1, 1, 1 in the y column. So it wouldn't be a one-to-one function with multiple y's there. So if the base is 1, f of x is equal to b to the x would not be invertible. So we're going to restrict the bases to have these limitations here in order to make f of x equal to b of x, b to the x power, an invertible function. So here's a few things we need to know about evaluating exponentials. Any real number raised to the 0 power is equal to 1. Any real number raised to a negative real number means you are putting this same number here without doing anything to it into the denominator. So this is sort of an order that says move to the denominator. Move all of this looking the same to the denominator. Then the other idea here is that if you have a fraction as a power, this is a root. Okay? So b to the 1 over a power means this is the 8th root of b. So this bottom number, I like to think about it as a root of the tree. Here's your root. If it's in the bottom, it's a root of the tree. So anytime you have a number in the bottom here, it's the 8th root of whatever this number is here. Okay, so we need to know those few things in order to evaluate exponentials. So 2 to the 0 is 1. 2 to the 1 is 2. 2 squared is 2 times 2. 2 cubed is 2 times 2 times 2. 2 to the negative 1 means I just take this 2 to the first power and put it in the bottom. 2 to the negative 2 means I take 2 squared and put it in the bottom. Now here's a root. Any fractional power is a root. So this is the square root because 2 is square root. This is the square root of 2. Let's look at this one over here. This being a 3 down here means the 3 would go here in the root position. This is the cube root of 2. All right, let's go back to this one. So this looks the same as this, except this negative is saying put whatever you have in the denominator. So 2 being a square root says put the square root of 2 in the denominator because I have a negative there telling me to put it in the denominator. All right, this one over here, this is the cube root of 2 because this 3 means cube root. This negative tells me put the cube root in the denominator. All right, so let's try this one here. 3 to the 0 is 1. 3 to the 1 is 3. 3 squared is 3 times 3, which is 9. 3 cubed is 3 times 3 times 3, which is 9 times 3, which is 27. 3 to the negative 1 means bring 3 to the first power into the denominator. 3 to the negative 2 means bring 3 squared into the denominator, which is 9. 3 to the 1/2 means the square root of 3. 3 to the negative 1/2 means bring the square root of 3 into the denominator. 3 to the 1/3 means the cube root of 3. 3 to the negative 1/3 means bring the cube root of 3 into the denominator. Right now, let's see what would happen if you had a fraction as a base. A fraction is still a real number, and it's a positive number. It's not 1 and it's not 0, so it qualifies as a base. So remember, when you take the powers of a fraction, so let's just look at this example here. I have 1/2 cubed. That means 1/2 times 1/2 times 1/2, which means 1 times 1 times 1 in the numerator and 2 times 2 times 2 in the denominator. All right, so let's look at this here. So I've got anything raised to the 0 power is 1. 1/2 to the 1 power is still 1/2. 1/2 squared is 1 times 1 in the numerator, 2 times 2 in the denominator. 1/2 cubed, we said, was 1/8. 1/2 to the negative 1 means I'm going to take the reciprocal, so it'll be 2 over 1, which is 2. 1/2 to the negative 2 means I'm going to take the reciprocal and then I'm going to square it. So that would be 4 over 1, which is 4. 1/2 to the negative 3 means I'm going to take the reciprocal and I'm going to cube it, which would be 8 over 1, which is 8. 1/2 to the negative 1/4 means I'm going to take the reciprocal and I'm going to raise it to the 4th power, which would be another 2 times 8, which is 16, and so forth. All right, we can do the same thing for 1/4. 1/4 to the 0 power is 1. 1/4 to the 1 power is 1/4. 1/4 to the 2 power is 1 over 16. To the 3rd power is 1 over 64. To the negative 1 power means take the reciprocal and still raise to the 1st power, so that's just 4. 1/4 to the negative 2nd power is take the reciprocal, square it, so that's 16 over 1, which is 16. 1/4 to the negative 3 power means take the reciprocal and cube it, which is 64. And then 1/4 to the negative 4 power means take the reciprocal and raise it to the 4th power, which is 100 and, 256. Okay. Now let's talk about log functions. So let's look at this first line here that says the logarithm y is equal to log to the base b of x is the exponent y to which the base b must be raised to get the given number x. Let's break down that line first. First, it says the logarithm is the exponent. So we're going to say this y is equal to this is an exponent. Then we say to which the base b must be raised. So I wrote that. To which the base b must be raised. So if it's raised to the y, this exponent we're talking about, since y is equal to log to the base b of x, I'm going to call that exponent log to the base b of x, since y and log to the base b of x are said to be equal. All right. Then it says the exponent y to which the base b must be raised to get the given number x. So we're supposed to get the given number x when we do that. So x is right here. So that means that everything else, this stuff here, must go away when we do that operation so that we're only left with x. So if that's the case, b raised to the log b reverses that whole operation, b raised up to a power, and returns you just this part here, x. Now, another way to look at that is in terms of something we already know about inverses. So here's a good example here. If we wanted to get this to just say x, I would need to apply the inverse of the square root in order to get this square root to come off of there so that I had an x left over. Well, we know just from doing it so much that that inverse operation is the squaring operation. So if I square that root x, it'll return me an x. So a squaring undoes a square root undoes a square. And it's that type of thinking we have to adopt here when we're talking about exponential functions and log functions. They undo one another because they are inverses. Okay, so let's try to do what we did in the last unit on finding inverses to this function y is equal to b to the x. So if I wanted to find the inverse function, I would have to apply step 1, which is switch the x's and y's. So I'm going to switch the x's and y's. Okay, then in step 2 is we need to solve for y. However, I need to have a way of solving for y there. I need to have a way of undoing that b to the y. I need an inverse operation. That inverse operation is taking log to the base b. So I'm going to do log to the base b of both sides to undo that. Log to the base b of x is equal to log to the base b of b to the y. All right, so that undoes everything and leaves me there with a y, which is what I want. So now I've got log to the base b of x is equal to y. If I wanted to use my f of x notation, I could have started out by saying, well, I could put it up one level higher. I could have started out by saying f of x is equal to b to the x. Then here's my y step. Now by the time I get down to having solved for y right here, I can now call that f inverse of x is equal to log to the base b of x. So what we've shown here is that this function, f of x is equal to b to the x, is the inverse function to this function, log to base b of x. So you could go either way. This is the inverse of this, and also this is the inverse of that, just like with square roots and squares. So it's worth spending a little bit of time on this at the beginning so that this starts to sink in. So I should have mentioned before, remember we already said that these are invertible functions because they're one-to-one. So let's go the other way now. Let's say we're starting with the function f of x is equal to log to the base b of x, and we want to find the inverse function of that. So we'll go through the steps. Step 1, replace f of x with y. Step 2, switch x and y. Oops, that's y. And the next step would be solve for y. Well, the only way we know of, we've got a new way now, we've got a new thing that we know how to do. In order to solve this for y, we've got to undo the log base b of y, so it just says y. Okay, so the way that we do that is to use the inverse function. So that means I'm going to raise both sides by the base b. Oops, that's a little b. Log to the base b of y. All right, and since these are inverse functions, this gets rid of all that. So I'm just left with y. So I'm saying b to the x is equal to y. All right, so like we do when we're finding inverse functions, once we've gotten to that step, we replace y with f inverse of x instead of y, and I've got b to the x. So we've gone full circle. So for finding the inverse of this function, we end up with this function. And like I showed in the previous steps, we could go the other way as well. If we're trying to find the inverse of b to the x, we're going to end up with log to the base b of x. All right, so there's one more thing, a couple more things on this slide let's mention. If the base of the log function b is left off, and you see that a lot, this is the most common base, base 10. Many times that will just be written log of x is equal to y. Base 10 is the most commonly used log, and that's a button we have on the calculator. All right, so the log button on the calculator is base 10. There's also a natural log button on the calculator. The natural log, this occurs in nature, that's why we call it the natural log. It's like pi occurs in nature. This is log to the base e of x is equal to y. This e right here is a constant. Okay, so we have a button for the natural log on the calculator because many of the word problems we can do in log units are problems based on real-world phenomena which have e in their formulas that apply. So the natural log, written y is equal to ln of x, ln meaning natural log, is base e. So I said e is a number which occurs frequently in natural phenomena, and it has a constant value of approximately this number here. So you can almost think about it sort of like pi. It's a number that comes up in nature quite a bit. Okay, sometimes you need to use a calculator to take a log or solve an exponential equation. So generally you can see that they've got the right buttons to use. Like this one right here is your plate for Desmos graphing calculator. It has ln, it has log base 10, and it has log base any base. If you want to get an e on this calculator, you've got to actually use the alphanumeric part of it, where you've got the alphabet showing, and actually use the e. All right, this one right here is an online calculator I use sometimes. This one has the e, the natural, for the base of the natural log function. It's got the log base 10, and it's got the natural log, which is the log base e. So the only thing this one doesn't have is the log base anything button like this one has here. So it just depends. The TI-83 or the TI-84 that we used to use in class in prior years had all of those things. Some of you may still have one of those calculators. But anyway, there's all sorts of calculators you can get a hold of these days online to do what we need them to do. And I'll let you know if we need to use one on a test or whatever, which one we're going to use. So let's talk about how to evaluate logs now in this table. So looking at the first column here, log to the base 10 of 0, the value of that is undefined. So anytime you have a 0 here in the input spot, you're going to be undefined. And let me just remind you of why that is the case. So if we're trying to find y is equal to log to the base 10 of 0, that means that if we take 10 to the y and 10 to the log base 10, we're doing the inverse operation. So this means that 10 to the y is equal to 0, and there is actually no number that you can raise 10 to that'll give you 0. So that's why this is undefined when you have a 0 in this position here. Okay, let's look at the next one here. So if y is equal log base 10 of 1, that means what power are we raising 10 by to get 1? All right, so we know that 10 raised to the 0 power is 1, so what we're looking for here is 0. So now let's look at this one. So if y is equal log base 10 of 10, we're asking ourselves, if my base is 10, what power do I need to raise that base by in order to get this number here? So the answer is 1. 10 to the first power is 10, so my log is 1. That's my exponent. Now here, we're going to ask ourselves, if my base is 10, what power do I need to raise 10 by to get 100? Well, 10 squared is 100, so my answer is 2. Now here, if my base is 10, what power do I need to raise 10 by to get 1,000? So 10 to the third is 1,000, because 10 times 10 times 10 is 1,000. So my my exponent is 3. All right, now here we've got a 10 in the denominator. So a 10 in the denominator is the same thing as saying you have 10 to the negative 1 power. These are two things are saying the same thing. So we're asking ourselves, what power do I have to raise 10 to get that 10 to go into the denominator? So the exponent would have to be negative 1. Raising 10 to the negative 1 power will put that 10 in the denominator here. So this is my log. Now here, I'm still base 10. What power do I have to raise 10 to cause 100 to be in the denominator? We can see that 10 squared is 100. So I would have to apply a negative 2 to that squared, to cause it to go down to the denominator. So my log is negative 2. So 10 to the minus 2, in other words, puts 10 squared in the denominator. So my exponent is negative 2. So now we're going to try this one without having all those pre-written things. So remember that whenever you have a 0 here, you're undefined. That operation is just undefined. Okay, now for the second one, we're saying if I have base 2, what power do I have to raise that to get 1? So whatever goes in that square is my log to the base 2 of 1. So that would have to be 0. 2 to the 0 is 1. Now for this one, when the base is 2, what power do I have to raise 2 by to get 2? Well, 2 to the 1 is 2, so my log is 1. All right, on this one, 2 is the base. What power do I have to raise 2 to get 4? So the answer is the second power. 2 squared is 4, so my log is 2. On this one, what power do I have to raise my base to in order to get 8? Well, this time it's 3, because 2 times 2 times 2 is 3. All right, now on this one, I've got to raise my base to some power to get the 2 to go into the basement. So that's going to have a negative on the power. So 2 to the negative 1 brings the 2 down below. So my log is negative 1. All right, so let's look at this last one here. 2 to some power is going to cause a 4 to occur in the denominator. Right, first of all, I have to square 2 to get 4, and then I would have to put a negative on it to get it to go down below. So the answer is negative 2. So I would write 2 to the negative 2 power is equal to 1/4. So my log is the exponent, which is negative 2. So this is going to take a little while for you to get used to thinking this way, because it's not something we do year after year as we're learning math, which, that's not a bad idea actually to introduce it earlier than we do, but it takes a little while to get used to thinking this way. So most of the work we do with logs, we do without a calculator so that we can learn what's going on. Sometimes the only time you really need a calculator is if we're doing real-world problems where you've got decimal numbers that you're working with that aren't easy to work with. So let's just go through these briefly, one at a time. So A says evaluate log to the base 10 of 10,000. So we're looking for an exponent here. So that means base 10 to what exponent gives you 10,000? All right, so I count my zeros here. So it'd be 1, 2, 3, 4. So that's 10 times 10 times 10 times 10. So my answer is going to be 4. That would be my exponent. Okay, looking at B, My base is 2. So what power do I need to raise 2 to get 32? So that's 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32. So that's 5. So our answer is 5. Okay, so we're asking ourselves, what power do we need to raise 2 to get 1/8? So first off, we want to think that 2 times 2 times 2 is 8. So that's 3. Bringing it down into the denominator means I make that 3 negative. So my log is -3. So on this one, I'm asking myself, my base is 3. What power do I need to raise 3 to get 243? So let's try it. So we got 3 times 3 is 9, times 3 is 27, times 3 is 81, times another 3 is 243. So that's 1, 2, 3, 4, 5. So the answer is 5. All right, so now let's go over to E here. Now what's different about this problem is that your base is bigger than this number here. All right, so in order to get the base smaller, you have to take a root. So, and you'll see the difference here. On this side, we went from smaller to higher, smaller to higher, smaller to higher, smaller to higher. Now here, this is bigger to smaller, bigger to smaller, bigger to smaller, etc. Whenever you're going from a bigger base to a smaller number, that means you got to take a root to get smaller, because our only options are either you raise it to a power or you take a root. Those are the only two things we do for these exponents and logs. So we know that the cube root of 27 is equal to 3, and that's the same thing as saying 27 to the 1/3 power is equal to 3. All right? So if 27 to the 1/3 power is equal to 3, then that means that 27 to the -1/3 power will bring that 3 down below, so it'll be 1/3. So this is the exponent we're looking for, -1/3. All right, so let's look at F. So once again, I have to do something to 16 to make it a 4. Well, you can probably see that that's a square root, right? The square root, though, is written as a 1/2 power. All right, and it's not in the denominator, so it's just a positive 1/2. So 16 to the 1/2 is 4, so our answer is 1/2. So here's another one like that. So I'm going from this big number, 64, and I need to get it to be a 4, and then I have to get it to go down underneath the line, so that means a negative. So if I think about 64, I know the cube root of 64 is 4, because 4 times 4 times 4 is 64. So a cube root is a 1/3 power. That gets me to the 4. But now I got to put a minus on there to get the 4 to go down to the bottom. So my answer is -1/3. Okay, so for H, I've got 5 as my base. I need to raise it to a power in order to get 625 in the denominator. So first we want to figure out how many times I got to take the power of 5 to get 625, and then I put a negative on it, and it brings it down to the bottom. So I've got 5 times 5 is 25. 25 times 5 is 125. 125 times 5 is 625. So that's 5 to the 4th power gives you 625. So this would have to be a -4 here to get the 625 in the denominator. So the answer is -4. All right, so one more. We've got log to the base 32 of 1/2. So my base is 32. I have to raise it to some power to get 1/2. So that means a root. I got to go smaller. So let's recall that 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32. So that means the 5th root of 32 is equal to 2. Okay, so the 5th root is written 1/5. So if I take the 5th root of 32, I'll get 2, but I want the 2 in the bottom, so I have to put a minus to get the 2 to go down here in the bottom. So my answer is -1/5.